Okay, this is an introduction to work, energy and power. We're sort of assuming that you've studied Newton's second law of motion and understand about forces there, but we'll just have a quick recap on that. So these are the sort of the components that are involved here in this section. So let's start with force. Force is something which is measured in newtons, and as I said, you should be familiar of this from uh, Newton's second law of motion. If not, then I think it's reasonably intuitive what a force is. But Newton's second law of motion basically gives us this: the net force applied to a particle is equal to its mass times its acceleration. And if the net force is zero, there's no acceleration. So that gives rise to a set of problems that we sort of regard as being equilibrium problems. Okay, so force is measured in newtons, it being and 1 newton being the amount of force needed to accelerate 1 kilogram by 1 meter per second Okay, so that is that. Let's think about energy, shall we? Energy. We're talking about mechanical energy, so there are actually two forms of energy. We have kinetic energy, which really results from its not only its mass but its velocity squared, in fact, half mv squared, and potential energy. Okay, now both of these are measured in joules. This is a kind of FMGs are going to be a force, isn't it? And height. Now, usually with the sort of problems that we're doing at A level, we talk about potential energy in terms of height above some reference point, probably the ground. There's other forms of kinetic energy, like springs and things like that, but we're not going to worry about those at the moment. So for potential energy, let's think about height. Something's height above the ground and its velocity, they're sort of tradable quantities, really, aren't they? We could, if it's got energy through being high, we could let it fall down and it would create velocity, but we'd no longer have the height. So the mechanical energy is the total of these two things together. We talk about force times distance. This is force times distance. mg is force, or equivalent to force, and h is a distance. This one's not quite so obvious, but if we do a bit of dimensional analysis on it, we can see that actually this, in terms of the units, this actually comes to the same thing. So we're measuring energy in joules. Very often kilojoules will crop up in problems, 1,000 joules, and we just have to make sure that we make the appropriate adjustment. Otherwise, our answer is probably going to be a factor of 1,000 out. So if we look at this kind of little model up in the top left here, if we project this particle up this slope here, then it's going to start off with some velocity v, and as it kind of fires up the slope, you're going to get to the top. Possibly by then the velocity will have expired, and what we will have is it will have all it will have potential energy, and then if it's allowed to roll back, well, we'll get to the halfway point. We have a mixture of potential energy and kinetic energy, and by the time we get to the bottom, we'll have used up all the potential energy in creating the velocity, and therefore the kinetic energy. So top's all potential energy, bottom's all kinetic energy, and somewhere in the middle is a combination of the two. So that sort of thinking gives rise to this. The principle of conservation of mechanical energy states that for a particle, providing no external forces other than gravity act to do work on it, the total sum of kinetic energy and gravitational potential energy will remain constant. So that's the mechanical energy will remain constant. Now, unfortunately, the problems that you're going to be faced in this section seldom have no external forces acting on them, there is always going to be something, and they might be positive forces. And what these will do is actually increase the total amount of mechanical energy. So some force that pushes a ball up a slope will increase that. The ball's at the beginning of the bottom of the slope, for instance, and with no potential energy, no kinetic energy, that force is applied, it pushes it up the slope, and therefore actually sort of increases the mechanical energy of the particle. So by in that case increasing the potential energy. So so that would be adding to the total energy. We also get kind of destructive forces, like if a particle's moving along with a certain velocity, if it's got friction to contend with, then that will actually reduce the amount of well, probably kinetic energy in that situation, but in general, it can reduce the total amount of mechanical energy. So by doing work on a particle, we can either increase or decrease the amount of mechanical energy, and that is a theme for, you know, pretty well all the problems that you're going to face in this section. So I mean, just looking at this sort of revised model here, we've got some force pulling this thing up here, and a force dragging it back, and possibly resistance, possibly would be friction. Okay, so these forces, when applied over a distance, will actually do work. And in actual fact, that's really how we work with work. Force times distance is joules. So that we measure work in joules. So if I apply a force over a distance, a known force over a known distance, then that product is the number of joules that is added into the mechanical energy or taken away from it, depending whether or not it's a constructive force or a destructive force. So that is the kind of basic idea of work. And as I said, this is a sort of common theme to all these problems, is the connection of work done and energy. So really it's all connected with this formula here. So the net work done on a particle, this is really work with a large W, is going to equal to the change in mechanical energy. So this isn't saying whether those are positive or negative, but essentially, you know, if we add, that'll increase. If we have a destructive force, then it's going to decrease, and typically there's going to be some combination of the two. Okay, so that is what we've got there. And the other one that we're interested in this little diagram is power. Now, power is the rate of doing work. We measure it in watts. So basically we're defining joules per second as being watts. And again, the problems might actually involve kilowatts, 1,000 watts. So again, be careful to make sure you do an appropriate adjustment. Right, so now the rate of doing work, well, that might be of interest, but generally speaking, what we're kind of more interested in is if power is work divided by time, yeah, joules per second, for instance, then work is force times displacement. Displacement divided by time is velocity. So power actually can also be expressed as force times velocity. And this little equation here is one which is going to be more common in the type of problems that you're going to be encountering. So that's kind of how that works. And so if we have well, power is something which, you know, a particle, a body will have. It's work that can be done to a particle, and more typically, it's actually a capability of the particle itself. And again, most of the problems you're going to be looking at maybe a motor vehicle, you know, a car. It's going to have mechanical energy. It will have work done to it, friction on the road, air resistance, and so on. But it will have some capability to drive itself. Okay, so that's a very common form. You probably you know that car engines are quoted in kilowatts, as well as brake horsepower. It's a different unit system, but you'll see the power quoted in kilowatts. Well, it'd be interesting exercise just to go away and look up a few of those, and then you might be able to work out some facts as to possibly how fast they can go. Anyway, I'll leave that thought with you. But a very common scenario is, you know, we've got some particle, the mass and a certain power rating, 10 kilowatts or whatever. It's driving itself along. It's experiencing a resistance. Now, if it's going at constant speed, there's no acceleration. So obviously, the force of the power and the force of the resistance are in that case equal. And if it happens to be its maximum speed, that's going to be the maximum power of the of that particular particle. So this is the sort of thing that you might encounter. Right, well, that's gone through those four components that we're interested in. There might just one other thing that's just worth noting. There's a nice little manipulation here that you might have seen. Starts off with this Suvat equation. We manipulate that, multiply both sides by a half m, and MAS, that's equal to force times distance. So force times distance equals a change in kinetic energy. All right, so that's a nice little thing. I mean, this is assuming that we're not increasing the potential energy of it, but it's also assuming that it's based on a Suvat equation. So just going back to our kinematics, if you have done that section, then it does beg the question, say, well, why or how are we assuming that acceleration is going to be constant? Very often in these things, basically it is constant acceleration. And if you're told that a force is applied over a given distance and that force is a fixed value, 250 joules over every 250 joules applied to slow a particle down, if you like, then, well, it depends. If you're giving it a force, then the force is probably going to be constant. If it's an amount of work, then you don't really know that that's going to be constant over that period of time. It's just a total amount of work over that distance that that's been applied. So probably don't worry about this too much at this stage, but in general, you may not be able to assume the acceleration is constant. So it's just something to watch out for. All right, so I hope that has been informative, and hopefully it'll set you up for having a go at some of the problems in this section. So thanks for listening.